Take a look at a word problem application now. So a population of bacteria, P, we're going to represent the population as P, is changing at a rate of dp dt is equal to 3,000 divided by 1 plus 0.25 t, where t is in days. The initial population is 1,000. Find the population after 3 days. Now, this is not a contrived example. Many times it's easier to describe how things are changing when you're looking at the derivative, right? Because we know derivative gives us an instantaneous rate of change. So this says that the derivative at any point is changing by, or the derivative is this, so the rate of change is changing by this much at any given t value. But we're not interested in the derivative at 3. We're interested in the population at 3. So I give you a derivative. You're trying to figure out what is that original function. So to do that, you need to find the antiderivative of this. So to reverse the derivative process, we're going to use an integral. So my p of t is going to be equal to the integral of dp dt with respect to t. So I have this, or in other words, you don't need to write this. You could write the integral of 3,000 divided by 1 plus 0.25 t dt. So you're trying to integrate this function. So to do this, we need to use u substitution. So we will let u equal 1 plus 0.25 t du will be equal to 0.25 dt. Or in other words, if I divide over 0.25, I'm really multiplying this by 4 is equal to dt. So 4 du is equal to dt. So I substitute things in. So I have a integral of 3,000 divided by u times 4 du. I can pull out the constant. I have 12,000 integral of 1 over u du. So this is my integral. These are parentheses, by the way. Now I integrate this, I get natural log. So I have 12,000 natural log of the absolute value of u plus some constant c. Don't forget the c. And again, I just skipped a step of distributing. This 12,000 we multiply by everything, but again, that's just a constant over there. So this is my function, p of t, but obviously we're like, well, obviously there's no t's, so I need to substitute this back in. 12,000 natural log of the absolute value of 1 plus 0.25 t plus c. So this is my function. Now the initial population is 1,000. When did we seen that before? Well, remember, if we have initial conditions, this is really saying that p of 0 is equal to 1,000. So that means I could solve for my c value because I have a specific choice because I have the information about the function at a value. So if I know that p of 0 is equal to 12,000 natural log of the absolute value of 1 plus 0 plus c, this is equal to 0. Natural log of 1 is 0. So I see that p of 0 we said is 1,000 is equal to c. So plugging that in, my function p of t is equal to 12,000 natural log of the absolute value of 1 plus 0.25 t plus 1,000. But I'm looking for the population after 3 days, or in other words, when t is equal to 3. I see that p of 3 is equal to 12,000 natural log of the absolute value of 1 plus 0.25 times 3 plus 1,000. So taking natural log of 1.75, multiplying that by 12,000, adding 1,000 to that, we get roughly 7,715. Approximately, that's the population, 7,715. Now, you might, again, this absolute value, you might see people who drop that. That's because in this case, the inside to a context will never be negative. For this to be negative, we'd have to have t be something negative, But if we're thinking about t as in terms of days, it doesn't make sense to talk about negative days if we're saying the initial is at 0. So just a small thing, but that's your final answer. That's what it looks like to think through a application problem from start to finish using a bunch of things that we have done so far this semester.